All right, help me out. How were you guys, or what were you using to find the equation for the line tangent? What's the first thing you did? Alternate definition. There are a couple different ones. Which one did you guys end up using?
Limit as x approaches c. No, x. X approaches c of f of x minus f of c over x minus c.
In context to this problem, this is the one that Ryan ended up using. Was there another one? Yes. The other one is you could use the limit as h approaches 0 of f of c plus h minus f of c all over h. But this is one of the alternate definitions. Now, how do we actually use it? How do we plug in? Well, first of all, what have I already plugged in? 0 for c. Why? Because that's the x value. That's the particular x value that I need. Okay, now how do I go plugging into the rest of it? F of x is... Are some of you like, aw, stink, I didn't need to actually cube that? But that doesn't mean that you couldn't have used another form, right? But why is this one easier than the other alternate definition? Yeah, you just get to plug in numbers. And you don't have to plug in a 1 plus h, or a 0 plus h, I should say, or an x plus h. Now, some of you did that, and that's okay. It works. It should have worked. But you didn't necessarily... Oh, did you guys notice my c that should have been a 0? Oops. Using this alternate form, we could have gotten there a little bit quicker. Because now what would we have done? Plug in 0, 0 over 0, keep going. But I can reduce the ones. What can I factor out?
X.
And I'm factoring out for the purpose of hopefully being able to reduce or cancel, right? So I have x squared minus 2 all over x.
Yeah.
Yeah.
Did you get the minus 1 at the end?
Oh, f of x is the first part, right? Minus f of 0 is the y value at 0. Does that make sense? Yeah. So then we go ahead and we've been good calculus students. We kept writing limits, so now we plug in 0 for x, and we end up with... How many of you guys got a slope of negative 2? How many of you guys got stuck somewhere cubing something ugly? Yeah, it happens. Katrina, do you have a question?
Oh, okay. I did it differently.
Which way did you do
I
it?
just did the power rule.
It should still work, but we weren't supposed to use shortcuts quite yet.
Oh, so
But the power rule, you would have gotten 3x squared minus 2, and you would have plugged in 0, and you still would have gotten negative 2.
yeah, so then I'm okay with it. Or,
Starting in section 2.2, yes.
okay.
Okay, sorry. Yes. But guys, are we done? We have this. What's negative 2 stand for? Help me out.
The slope of the tangent line.
The slope of the tangent line at 0, 1. Or we could say the slope at x equals 0. Now, if they want the equation of the line, that's not enough. So how do we keep going? Point slope form. Y minus, technically, f of, don't die, f of 0 equals f prime of 0 times x minus 0. Does it make sense why each of these spots are filled with what they are? Usually it's y minus y1. Who is this? y1. It's the y value of the point. X minus 0, that's the x value of the point. And then f prime of 0 is the slope, so all I have to do is plug it in. Y minus my y value equals m, which I found up here, x minus 0. And technically, as we saw yesterday, if it's not multiple choice, stick it to the man, you're right. I don't quite trust you enough to say that you'll always get it right if you keep simplifying. But if it's multiple choice and if all the answers are y equals mx plus b, are you going to keep going? Yes, you're going to keep going and you're going to make it match. Now, how am I going to graph both? I already have my function. What else do we need to graph? Now we have to get y by itself, right? Yeah. Okay. We're getting y by itself. Hopefully we can do it correctly if we're all working together, not make any silly mistakes. Wouldn't it be negative 2x plus 1? Double check, is that right?
Yeah.
Yeah.
Okay, now get water today. And if I graph? Does it look to skim the graph at 0, 1?
Yeah.
Looks like it to me, yeah? So we can say, hey, there we go, we got it, and we're good. Now, is this a proof? No, this is not a proof that we did it correctly, but is it a demonstration that we seem to be right? Yes. It demonstrates that we seem to be spot on with our line tangent to showing the slope at 0, 1. Questions, because this was a big part of what last night's homework was. Okay. I know a lot of you guys might have gotten stuck on the last 4 problems of homework because it dealt with a little bit of notes that we didn't get to finish up very well at the end of yesterday. And then some of you guys might have gotten stuck where it said something like, hey, given these graphs, sketch the graphs of the derivatives. Ugh, that's a hard topic. We're going to get into the evens of our homework in just a second, but first, the last 4 problems dealt with this page. Some of you guys did not get to get it written down yesterday, so let's go ahead, keep your spirals closed because we're going right back to check homework. So let's go ahead, in our composition books, let's make sure we have this final idea from yesterday. This final idea from yesterday. I'm going to kind of reword that just a little bit. I am putting a box around it because yeah, it should be. At least until I do one. Putting a box around him because he's especially important. He is forever number, where are we at? 8? Two exceptions we started talking about yesterday. I can use CONT to be continuous. I can use DIFF to be differentiable. Okay. At sharp points. Bless you. Bless you. Or at vertical tangent lines. There are technically a few different categories of sharp points. There are cusps. There are corners. But we're not going to stress too much about the different names. But there are 2 different things that can happen in continuous functions that cause the function to not be differentiable. One is sharp points, and the other is vertical tangents. I wanted to kind of reword that, or at least rework that a little bit so I can add in just a little descriptor of each as to what's going on. And we'll hopefully be able to see a couple examples of this as we check our homework. Hopefully vertical tangents is the one that'll make the most sense because the derivative is the slope of the tangent line. What is the slope of a vertical tangent? I know it's vertical, but what does it actually equal? This is 0. 1 is like up 1 over 1. Sorry, up 1 over 1. Undefined, but specifically what kind of undefined? This is like a 0, this is like a 5, this is like a 50, this is like a 500, this is like a 5,000, this is like a 5 million. It's infinite. Wait, how can a slope be infinite? Well, derivative is really just a limit. Can't limits equal infinity? Or negative infinity? Yeah. So if limits can equal infinity or negative infinity, then derivatives could possibly end up equaling infinity or negative infinity, at which point we say the derivative does not exist because the slope is not a constant. Hence why all the way from Algebra 1 or maybe even pre-algebra you guys have learned vertical lines have undefined slope. But technically, undefined slope is infinite slope. So remember, your derivative is really a limit. If your derivative is infinite, if the limit ends up equaling infinity, you have a vertical tangent, and we say technically the function is not differentiable there. Because we cannot state the slope as a constant. What is going on? Sharp points. Sharp points. Long story short, the limit we'll say it this way. Hold on. Remember, the derivative is defined as a limit. I'm going to say the one-sided derivatives do not agree. The one-sided derivatives do not agree. What do I mean? The one-sided derivatives that are really limits, so the one-sided limits do not agree. Sharp points. What's going on is one-sided limits are not agreeing for the derivative. So therefore, the derivative would not exist because if the one-sided limits don't agree, the limit does not exist, hence the derivative does not exist. But long story short, if a function has a discontinuity, is it differentiable there at that point? No. If a function has a discontinuity, it will not have a derivative, it will not be differentiable there. If a function is continuous and has a sharp point, it will not be differentiable there. If a function is continuous and has a vertical tangent line, it will not be differentiable there. But it'll be differentiable everywhere else. The derivative will exist everywhere else. And if you are ever told a function is differentiable, and this is one of those things as we get to AP questions, they like to say if f is differentiable. If they say that, we can assume, we know for sure the function must be continuous. If it's differentiable everywhere, or if it's differentiable at a point, it has to be continuous there. I know it's kind of weird, it's a weird forever card, but basically, continuity, points existing, limits existing, and them agreeing on original function, differentiability, derivatives existing, the limits existing, and them agreeing. So they're similar, but they're not exactly back and forth in the sense of continuous always differentiable? No, continuous usually differentiable. Watch out for a couple special cases. All right, with that, let's go ahead and go to our homework. And let's check the evens. You guys have your colored pens out. Quick heads up. When we check your chapter 1 homework, when we checked your homework for chapter 1, we did not grade whether or not you were grading your homework. But guess what we're starting with chapter 2? If you're not grading your homework, you're going to get points off. So, you cannot, at any point this year, if you lose any points, come and be like, wait, but I corrected in pencil. That is not acceptable. You know it, okay? So we're correcting with colored pen. Not black, not gray, not highlighter. Something that is visible. As long as you're correcting in colored pen, we're good to go. And could you be correcting your odds the night before? Yes. Why? You're trying to show yourself what you need to work on, okay? All right, what's our first even? You guys help me out. I don't have it memorized. 14. 14. Final answer is 7.
If we got it right, do we mark anything or just?
You do a check mark if you want to do it that way, because that way I'm like, oh hey, they're actually great.
Okay.
You do a check mark to get it right. Yeah. I am downloading it so you guys be able to see it longer. And you guys know how to use my videos, right?
No.
Yeah.
If you go under website, CalcAB, scroll to the bottom, it says something like lecture videos, or you just search Miss Dulac HTS YouTube, and then go under the CalcAB playlist. Okay. What next? 38. You can also watch the video and you can pause it. I do this so that people who are gone can correct. Oh my goodness, this is very long. There it is.
Can you explain that?
I think you guys might have gotten stuck at 37 to 40, yeah?
Yeah.
Okay, take a second. Take a second. Graph the right graph for 38. We'll come back to these in just a moment. Remember, I actually had it on the notes and I was ready to talk through with it. Or talk through them with you. And specifically, where is this? This piece of the derivative is f prime of x equals -1. And this piece is f prime of x equals +1. And technically, if you want to think about it in an algebraic sense, it'd be f prime of x equals -1 for x less than 4, +1 for x greater than 4. And if you notice, there is no derivative at x equals 4. We'll come back to number 38 in just a moment, but let's keep checking our evens. We have number 40 also, yeah? I know, 37 to 40, don't worry, I was already waiting. Try to help on them. The number 40, go ahead and get the right answer. It goes through 0, 0. And as some people are sketching, where am I headed next for evens?
46.
Do we have it okay? 46. Final answer is f of x equals x cubed and c equals -2. You had to look inside a definition formula. You had to look inside a definition formula and pull out what function was in there and what c was in there. What's the next one?
66.
66. Let me give you a couple seconds. They're using an alternate definition, right? They're plugging in with the function that was given. There's a c that was given. Very similar to how we started off class today. Very similar to how we started off class today. Except they would have gotten down to here. This is a huge jump for some of you. A huge jump. How would I have shown work? What would I have told you to do? Multiply top and bottom by both of the little denominators that are causing me problems. And then as we distribute, 4x times 1, the first one, 3 over x, the x's cancel, the 4 remains, 4 times 3 is 12. As we distribute to the next one, the 4's cancel, 3 times x is 3x. And then just write it next to, pull out a 3, reduce, reduce, as x goes to 4, plug it in, Angela.
On the second to last step, what I got at first, I pulled out the 3 and I had quantity. I
4
pulled out
minus?
and I had quantity, 4 minus x. Can you just take out a negative?
Yeah.
Is that what?
So you could do it separately and pull out the 3 first and then pull out a negative. The reason why they pulled out a negative right away is they were like, wait, I don't want the x to be negative, so then they wanted to switch it around. But yeah, you can do it one and then the other. So final answer is -3/16. What's our next one?
76.
It's right over here.
And 70.
These were your last ones you guys were able to graph on your graphing calculator based on what we just put on that card. Looking at this function, where will 4x over x minus 3 not be differentiable? Do you see any sharp points? Nope. See any vertical tangent lines? No, I make it steep, but it's not going to go straight up and down. But what is our one problem? We have a discontinuity at 3, which means the function will not be differentiable at 3. Wherever the function is discontinuous, it is also non-differentiable. And I think you guys had 78 also, right?
Yeah.
So then for number 78, f is differentiable for all x not equal to 1. How come? Because 1 is a discontinuity. 1 is a discontinuity. So if it's a discontinuity, you can't have a derivative. And if you want to think about why, sometimes the derivatives don't agree, but that's not necessarily the answer. If it's discontinuous, we can't say that there is a derivative approaching from both directions of a discontinuity. That's not going to be proper. That's not going to be legal. And if you guys notice in number 77, why is it non-differentiable at 0? Because there's a sharp point. Technically, we call it a cusp. There's a sharp point. And then number 75, differentiable everywhere but 5. The function exists there, but there's a sharp point. The derivative will not exist. Let's go ahead and remember, if you guys have questions on odds, please, please, please come find me. I'll be here during lunch. I'll be here after school. Or grab a classmate and be like, you want tutoring hours? Can you explain this to me? There we go. But I did have this ready for us to talk about because I knew that we were a little bit stuck. What problem numbers were these again? Number
7 through 40.
37 through 40. Okay. You guys, oh my goodness. Orientation is up. You guys were supposed to write down the directions and the problem, so help me out with what you were given. You weren't given derivatives. You were given originals. If you want to go in your notes and write this down, that's great. We're going to actually spend some more time on this soon. You can also just work on it in your homework, and that's fine as well. So it's up to you as to where this goes. Technically, this is for numbers 37 and 40. Sorry, 37 through 40. What were you given in number 37? What did the graph look like?
A parabola.
A parabola centered where-ish?
4. 0,
Four.
4, comma 0.
4, comma 0. Okay. Where does it hit the y-axis?
It did. It's x squared though.
I'll just do that approximately. Okay, we're orienting because I am really annoyed. There we go. Better or worse than the beeps?
Better.
Better. Huh. Gets a little annoying to me after a while. Oh, that's helpful. There we go. Because last year there were the beeps. You guys were all transfixed by the orienting of the board. Alright, that's better. Okay. You guys have already seen the answer to this, but you might have been completely perplexed. This is the graph of, I think they called him F. We were trying to find the graphs of the derivatives, so hence F prime. Yesterday we saw that the increasing, decreasing, constant nature of F determines the y values of F prime, and vice versa. So, question. How is F behaving from negative infinity to 4? Remember, read it left to right. Decreasing, right? So the function is decreasing. Then, from 4 to infinity, increasing. What's the one that I've left out? At 4. So, my function is going down. And how can I see that? My slopes of my tangent lines will be negative. Then my function is going up. My slopes of my tangent lines will be positive. What will be my slope of my tangent line at 4? 0. So yesterday we saw that to graph the derivative, we have to think about y values as slopes. So you guys just told me that the slope at 4 is 0, which means at 4, the y value of the derivative will be 0 because 0 is his value. And then if the function is decreasing before then all of the derivative values or y values must be negative. Negative. Why are you going down? Negative, because they're negative y values. Negative y's. And specifically, if you want to think about it, they're little baby negatives, so really close to 0, then they get more and more and more negative, more and more steep. Hence, I'm just going to be going more and more negative as in down.
It'd be a straight line.
Mm-hmm. It'd be a straight line because it's decreasing at a constant rate. Or I could say velocity is decreasing at a constant acceleration or deceleration. But that's for another day. And then my slopes go positive, which means my y values go positive at a constant rate as well. Hence why for number 37. When you guys were graphing it, it should have looked somewhat like a straight line. This is not a tangent line, and technically maybe it should be a little bit higher up. I think I was a little bit skewed on exactly where I was drawing it. But long story short, it's going to be a straight line. Because the slopes, as you go to negative infinity, the slopes are decreasing or going down. And as I go to positive infinity, my slopes are increasing or going up. Now, number 38, what graph were we given?
Which was absolute value of x.
Centered at
4.
4. If we're trying to think about slopes of the graph, why is this one actually a little bit easier than the other one? How many slopes are there? 2. Because how many lines are there? 2. And lines have a constant slope. And specifically, if you guys looked at your graph, you should have been able to go ahead and as you approach negative infinity, or as you come from negative infinity, the slope, I think, and you guys might have drawn it a little bit better, I think, was it down 4, right 4? So rise over run, we knew exactly. Rise over 1 was negative 1. So f prime is going to be negative 1 for all x less than 4. Why? Because all the slopes are negative 1. The line has constant slope of negative 1. And then after x equals 4, now it's rise 4, run 4. That's going to be a positive 1 for x greater than 4. Now how do we graph this? It's a piecewise. For all x less than 4, it's just going to be a straight line. For all x greater than 4, it's just going to be a straight line at positive 1. And why were there holes? Because as you come from either side, the slopes do not agree. One-sided derivatives don't agree. The slopes do not agree, so the derivative does not exist at 4. Sharp point, they do not agree. That's what's going on with any sharp point. Now, kiddos, I know we have 39, I know we have 40. However, I am going to go ahead and pause real quick. We'll go over 39 and 40 at the beginning of tomorrow so that you guys can go back to your homework and peek at them. They get a little bit harder. They're a little bit more curved. But I do want to go ahead, and this is something we're going to be working on for like a couple of weeks and still referring back to for the rest of the year. So it's not an easy idea. Visualizing the graphs of the derivatives from the original. There's actually this whole like graph matching, card matching activity some of you might have heard of before to help you work through it. So this is just an introduction. Don't stress if you don't have it fully down, but hopefully we have a good intro. But we do need to go ahead and get into section 2.2. Nice thing is we're doing section 2.2 today and tomorrow. There are, I should say, a few ideas in section 2.2 having to do with rates of change, average rate versus instantaneous rate. A little bit of physics, just a little bit. A little bit of application. So before we get into the section too deep, some of you guys are going to be like, why on earth are they giving me stuff about velocity? What's going on? So I'm just trying to give you a quick intro as to one application of derivatives. The primary mathematical tool of calculus is the derivative. We've kind of talked about him. We talked about his verbal description, talked about his definition. But what is he used for? The derivative is used to calculate and study rates at which one quantity changes relative to another quantity. One you guys are most familiar with would be like miles per hour. That is a rate of change talking about how many miles you would go in 1 hour, right? Miles per hour. So per unit of time. What would your change in distance be? If you've taken any physics, you know that miles per hour is not the only way of talking about velocity with change in position over change in time. It could be feet per second. Don't usually have per minute, but we could. But this whole studying rates at which one quantity changes relative to another, that can be applied to economics, that can be applied to physics, that can be applied to chemistry, that can be applied to all sorts of different things. Derivatives are applicable across many fields. History, there's this whole battle between Newton and Leibniz, and maybe we'll come back to that at some point. We're just kind of talking a little bit further about calculus, where he comes from, etc. But when you see rates of change in section 2.2, that's one of the, or I should say, that is the primary application of derivatives. So that's why they're introducing it. Okay? But the nice thing is, some of you guys are like, wait, you said section 2.2 we'd have shortcut rules. Wrong one. Woohoo! Struggle. Why are you still not working? And so some of you guys saw these this summer and understood them. Some of you guys saw them this summer and never understood them. And some of you guys saw them this summer and understood them and then promptly forgot them. And these shortcut rules allow us to not have to stay with the limit definition in solving derivatives. Bye, guys. And from yesterday, we learned some notation to kind of help us out for each of these rules. Because we talked about if we need to derive a function, we can use the notation d dx. When the function is in terms of x. If it was in terms of like t for time, we'd do d dt instead. That's notation for to take the derivative of a constant. How do we talk about constants in math? I don't know, see? What's the derivative of any constant? 0. How come? Y equals constant is a horizontal line. What's the slope of any horizontal line? 0. That's one way of looking at it. Another way of looking at it is, well, let's do the power rule first, then we'll come back. Power rule, d dx of any x to any numeric, or constant, I should say, power or exponent. We've kind of been introducing this one for a while. Bring down the exponent, keep the x, take away 1 from the power. Right.
Does the power will only work for integers or for all?
All real numbers. All real powers. But it does not work for variable powers. Hence why I was trying to say the constant. So then after the power rule, what's another way of looking at the constant rule? We could say that it's c times x to what power? 0. Bring down the 0. Oh, that makes sense. So there are two ways of looking at the constant rule. Constant multiple rule. If I'm taking d dx of a constant, that's an x. He's not looking much like an x. Hold on. Of a constant times x to a power. When that n comes down, what does he end up multiplying by? So the c can just go ahead and remain in front. N, x to the n minus 1. And technically that could be true. That's just one example of the constant multiple rule. If I was to generalize this just a little bit more, I would say something to the effect of d dx of c times any function. That c can just remain, and I take the derivative of the function that it's after. That's a more general way of saying the constant multiple rule. But basically, if you have a constant in front, just keep them in front and multiply by any other constants that come to join. Sum and difference rule. If I take the derivative of two functions being added or subtracted, which could be something as simple as x squared plus 5x. It could just be two pieces, like a binomial. We are allowed to, with addition and subtraction, or I should say or subtraction, we'll do plus or minus. We're allowed to take the derivative of one piece, add or subtract based on context the derivative of the other piece. We can take the derivatives separately. And then put it all together and then be done. And then last but not least, sine and cosine. The derivative of sine. Now, you guys know there's more trig than sine and cosine, but we're just starting off with the basics. And the basics include sine and cosine. They're the fundamental building blocks of the rest of trig. Strange as it may seem, the derivative of sine is really just cosine. And the derivative of cosine is really just negative sine. And technically we could do, I didn't make you guys do any of these, we could do the limit definition on sine and cosine. We'd have to use like composite argument properties from last year, the whole sine of a plus b sort of thing for x plus h. It would have been nasty. But we would have gotten these same answers. But it's kind of nice if we can just memorize them. It makes things a little bit easier. How important do you think these basic rules are? Very important, because we're not going to stick with that limit definition the entire year. We have to remember and have to be able to apply it the entire year. To interpret a question that might have it, however, we don't have to stay stuck solving derivatives that way. This is for every card number, I think 9, right? Question. How long would this derivative down here, the first example, have taken if we had solved it with the definition? Negative 3x to the 12.
A while.
You guys did a cube today and you were like freaking out, right? So, negative 3x to the 12th, that'd be ridiculous. However, what can we do with power rule and constant multiple rule technically? Bring down the 12, multiply it by the negative 3, right? Which would end up being negative 36. X to the, what do we do to the power? Guess what would happen after you raise this nastiness in the limit definition to the 12th power and simplified? You get that nice easy answer that we're going to now be able to start doing fast. Alright kiddos, I'll see you tomorrow. Homework due on Friday. Homework due on Friday. Last night's homework had some tricky stuff, that's why we took a little bit longer on the thing.